Okay, so first of all, I want to briefly summarize what we have covered so far. So the first thing is about the mathematical background. That was the beginning of this class. So for that, we actually talked about convergence, right? And limits, sequences, those kind of basics, and also the small o, big O notations. Then we talk about the four modes of convergence for a sequence of random vectors, not real vectors, but random vectors. So we have the strongest one, almost sure convergence, which is, very strong because you need the convergence to happen in every realization. So it's not so commonly used, mostly as a mathematical tool, but not as a direct result we require. But something more relevant is the convergence in probability, which is used a lot. In statistics, a lot of the arguments we make say, oh, this is a good estimator. We talk about convergence in probability. And also when we say high probability, something holds for high probability, it is also related to convergence in probability. Another thing is the convergence in quadratic mean, or the special case for convergence in the rth mean with r equals 2. That is more about average instead of high probability. So in many cases, we can also say that, okay, we can prove the convergence in quadratic mean because that would imply convergence in probability. Okay, under some conditions. Another thing is regarding the convergence in law, which is the most commonly used one when people say asymptotics. So in that case, we are interested in the distribution or limiting distribution behavior of a statistic, not just its limit. We know, okay, the sample mean by law of large numbers will converge to the population mean in probability and also almost surely. So that's a very strong result. But it doesn't say, okay, how is the sample mean distributed around the population mean? We don't have that information. And the central limit theorem basically provides that information. Okay, so that's why the central limit theorem is very useful. And it is also very useful because when we want to say establish a confidence interval about our parameter based on our estimator, central limit theorem provides the very convenient way because you can just use the asymptotic distribution to construct a confidence interval. So that is something you have learned from undergraduate class, maybe one-dimensional central limit theorem. So here, the central limit theorem in our case is multidimensional. And we also extended this to cases where we don't have IID fully hold. So we can have independence, but not identically distributed. And for that, the Lindbergh-Fowler theorem is for that purpose. And you need to check the Lindbergh condition. Or you can check a stronger one, which is called the Lyapunov condition, if this is easier to check. So the idea is to make sure that the theorem applies. So essentially, the idea is, even though you don't have identically distributed random vectors, but you hope, or random variables, but you hope that no one really dominate in the average. So you can still have an effective average. That's the most important thing. So, the magic in the central limit theorem is that no matter what the distribution each random vector takes, but as long as the distribution is not too, uncontrolled, in the sense that it has maybe undefined second moment, right? It has too wide as the variance, except as long as the distribution is somewhat concentrated, then by having many of your random vectors, their average will behave like normal distributed. That's the most important thing. But you need to have enough of them by taking the average. So the Lyapunov or the Lindbergh condition is just to guarantee that no single thing dominates. Okay, that's the rough way to say it. And you see that this Lindbergh-Fowler theorem is useful for deriving asymptotic normality for the least square estimate for the slope in linear regression. Okay, then going beyond this Lindbergh-Fowler for independent but not identically distributed things, we move on to the so-called stationary M-dependent sequences. That is also in our previous lecture. So what this is about is that you drop independence, but you keep identical distribution. So in this case, you need the dependence to be not so strong. It's only limited within a certain range. So like within M, right? M dependent means that within M, if the random vector are within M in the order, in the sequence, then they have dependence. But beyond M, they don't have sequence, they don't have dependence, to become independent. So that's why if you have many of them, then the majority of them are independent. Only a minority of them are dependent. So their dependence doesn't affect the central limit theorem that much. So the most important result for applying this is that you need to update, you need to change this, the variance term in the asymptotic normal distribution by adding additional term. And this additional term is actually the dependencies among your sequences. So maybe this is like the first draft. Let's go to the formal thing. Formal things here. This is the result of the central limit theorem extension for stationary M-dependent sequence of random variables. So essentially, this sigma square is what you already have in the central limit theorem. But this additional term is about the dependencies, right? Covariances. So gamma k means the covariance of two random vectors, two random variables. We're talking about one dimension, two random variables k apart. Okay, so gamma 1 is, say, xi and xi plus 1, their covariance. Gamma 2 is xi and xi plus 2, their covariance. You add up to gamma m. Because beyond gamma m, if it's like xi and xi plus m plus 1, they are independent. So their covariance becomes 0. So you see, to interpret this result, what it means is that if your random variables are not independent, but they are dependent, then you will have a less nice limiting distribution because it's still normal, but the variance is bigger, right? Having a bigger variance means what? Means that xm bar is less concentrated on your mu, right? So then using xm bar to estimate mu, it's a worse estimator. It's less efficient because the variance is bigger. That's it. Because, ideally, we want this variance to be as small as possible because that will indicate the concentration of xn around mu. Okay, so that's the intuition I hope to provide. So essentially, something you should be aware of. This is the maybe I should come back to this one while talking. So I think this is a general principle in statistics, right? How good is an estimator? We considered several things. First of all, is your sample size large enough, right? Because we need that an estimator to behave well when the sample size is large enough. And consistency is about that. Essentially, you want your estimator to go to your true parameter as the sample size goes to infinity. And this is different from, I think, a question asked by someone here last time is about the difference between consistency and unbiasedness. Unbiasedness is for any finite n, while consistency is for n goes to infinity. That's the difference. Okay, another thing which is something to consider about an estimator is its asymptotic distribution. That is, subject to some, we multiply by root n here to stabilize it because we know that as n goes large, xn bar minus mu will go down to 0 in probability, right? So we multiply this shrinking difference by root n. And then by the stabilization, actually we have a stable limiting distribution as n goes to infinity. So if we want to compare two estimators, one thing is to consider comparing their asymptotic variances. If both are consistent, but one estimator has a smaller asymptotic variance, it's regarded as a better estimator. Okay, and if you're doing a statistical test, then it will be more powerful as a test statistic, because it can better distinguish the parameter value under your null hypothesis and alternative hypothesis. Okay. Now, central limit theorem is almost done. And I want to say that this stationary M-dependent sequence central limit theorem result is useful because then you can study statistics like this, right? Sn is a sum, I from 1 to n, of xi times xi plus m. So in this case, xi and xi plus m are independent. They are IID. But in the sum, the terms you are summing up, they are not independent because they may share the same xi plus m. For example, one term could be xi times xi plus m, and another one would be xi plus m and xi plus 2m. Then these two terms will share the same xi plus m. So they are not the products, they are not independent. So therefore, we have to say define yi as just xi plus times xi plus m. And then for these yi's, they're not independent, but they follow stationary m dependent sequence. Right? That's why we can apply this result and to get the asymptotic distribution down here. Right? So essentially, this result opens the door for more derivations you could do regarding asymptotics of your statistics. Okay, so that's the recap. And finally, I want to say, and the rung of successes is another application we talk about. If you have a sequence of coin tosses, you want to ask how many consecutive rounds do I have, right? That's another example we gave you last time. So you can rewatch the video. So besides what we just said, another very important thing is the Slutsky theorem, which is something we already mentioned in lecture 1, but we also touched upon it again last lecture. It is a way for you to use your individual asymptotic results to assemble them into the asymptotic distribution for a new statistic. Basically, it says that if you have two convergence, one is a convergence in law to a distribution or random variable. Another is like the difference between two random sequences converging to zero in probability. Then you can transfer the result from the first sequence to the second sequence. So you can just apply this result. So maybe it's not easy to derive the asymptotic distribution of what for yn independent or for yn specifically, but it's easy to derive something from a simpler form xn, and you know that x and y's difference is going to zero in probability. Then you can just use the result for xn as the result for yn. Okay, another thing is regarding the joint thing. So if you have separate convergence in law, and the second one is convergent to a constant, not a random variable or distribution, then you can have the joint distribution. Joint random variable, that joint distribution of random variable derived. So you're still keeping x and then c. But if the second one, like I said here, is not a constant, but it's a random variable, then we don't have that. Because in this case, you need to consider independence or dependence between x and y and x and y. And the first statement continuous mapping theorem is about, say you already have xn converge to in law to x, but then you apply a continuous function, right, to both ends, then you can have this after transformation, you still have the convergence in law. But you need to have a condition, that is the continuity set of the function or the limiting random variables in the continuity set with probability 1. You need to worry about this continuity issue there. Okay, Slutsky. So with that, then something we actually showed you is this, sample moments. So in this case, Sx squared is the sample variance, basically. Or I should say it's the sample second moment, and Sy squared is the sample second moment for y, for x and y. And so basically here we're considering a bivariate case, x1, y1, x2, y2, and the sample from a bivariate distribution with finite fourth moments. So last time we actually derived this asymptotic result for these moments, and we use this result to derive this. To derive what? The asymptotics for the sample correlation coefficient. Pearson correlation sample version, convergent, how is it behaving around the population correlation coefficient? This is what we derive. And we can see that this asymptotic variance would depend on actually the fourth moment of this bivariate distribution. Luckily, if the sample is drawn from a bivariate normal distribution, if you have that, then you can much simplify the asymptotic variance to a great degree. This is all you get. It's because your bivariate normal is very nice since its higher moments can be defined just based on the second moment, right? So you only need to go to second moment to define a normal distribution. And using that property, essentially you can see that the asymptotic variance of sample correlation coefficient only depends on the population correlation coefficient. That's it. Okay, so this is what we did. And it's an application of the central limit theorem and actually Slutsky. Okay. And something I didn't say yet. Oh, and also the delta method. That's something we said last time, right? Delta method is also a way to make central limit theorem easily applicable. That is this. This is the delta method. Delta method says that you already have the convergence or asymptotic result for xn. You want to show what is for gxn. So you can apply the same g function to xn and to mu. And you can keep the normal distribution as the limiting distribution, but you just need to modify the asymptotic variance. Essentially, you need to apply g dot mu, which is the gradient or derivative of g at this mu. And you need to multiply that. This is the vector form. So you need to left multiply and right multiply your original covariance matrix in the asymptotic normal distribution by multiplying it on both sides. That's what you do. But if it's just one-dimensional, then if x and mu are both one-dimensional, then this sigma matrix will become a scalar, sigma square. If that's the case, you just multiply g prime g dot mu square. That's it. So yeah, what I just said for deriving these sample moments and the sample correlation coefficient, we use the delta theorem again and again. So basically, we talk about all these important things to do for deriving asymptotic distributions based on central limit theorems. Something we haven't said yet is the very important result for maximum likelihood estimator. So it has its own result, but we haven't touched upon that part yet. We'll do that later. Okay, so any questions we have? Something I also want to emphasize a little bit is that the delta method can help us find this variance stabilizing transformation. So the idea is that, yes, you may have some good result for, let's see, this one. You may,
Sorry,
sure.
about the delta method. I noticed we have to require the G to be continuous. What if we weaken it to be like probability, like it's continuous equal 1, or most everywhere continuous?
You are talking about the delta method here.
Yep.
So it's continuous in a, so we're just saying that it's a continuous in a small neighborhood, but this continuity has no randomness involved because it's a function. We're just talking about G. It doesn't involve the random variable.
Oh, I see.
Yeah. Right, it's about the function. If it's not continuous or it's not continuous in the neighborhood of your parameter of interest, it's not a good function, right? It's not a function, a transformation you can apply. Yeah. Thank you. And so, yes, this is the thing to start with. So basically, we have this asymptotic distribution for sample correlation coefficient. And variance stabilizing transformations idea is to get rid of parameters because we don't know their values, to get rid of parameters in the limiting distribution. Try to make the asymptotic variance 1. So the idea is, how do I find the function g so I can transform r and rho both by g? And then I can multiply g dot rho on in the variance, right? We'll multiply G dot rho square here, and then we can use that to make this variance a constant instead of something depending on rho. That's the idea. And this can get us to this very interesting transformation. So you can see that by defining G rho as this, after the transformation, the limiting distribution becomes N01. So we no longer have rho in the limiting distribution. This is the variance stabilizing transformation. Okay. That was the recap. Okay. Then we opened a new topic at the end of last lecture, extreme order statistic. So now we are concerning about the distribution of the minimum or the maximum of a set of random variables, a set of IIDs. Okay, we're worrying about the maximum. How does it estimate the upper bound of my random variables support, its distribution support, and how is the minimum estimating the lower bound? Okay. So this is the crucial result we will use. 1 plus c over n, the sum raised to the power n will converge to e to the c. So as you have n in this denominator and you have n in the power. So this is the form we will create for deriving asymptotics because you see in the limit n is gone. So more generally, we can actually change C to Cn as long as Cn converges to a constant. We can change n to Bn as long as Bn diverges, and the limit will still hold. Okay. This is the thing we start with. And first result we showed you is this. X1 to Xn are IID uniform 0 to 1 random variables. What is the asymptotic distribution of the maximum? So last time we spent some discussion to say, okay, we start from this very central result, basic result, that is for IID's maximum, if a maximum is under some upper bound, less or equal than something, it means each of the random variable is less or equal than the same thing. Because they're IID, then I can just take the probability of one of the random variables under T and raise to the power n, right? As long as T is within the range 0 to 1. Okay, based on this result, and based on that asymptotic result we want to apply to, essentially we found this result. This is what we derive. And we are deriving this based on the CDF function, the limiting CDF function. Essentially, we are trying to say that, okay, if we want to find the distribution of this form, an times xn maximum minus bn. So the question is to find what is an, what is bn. We first set bn to be 1, the upper bound of the uniform 0 to 1. The question is what is an? And then we know that based on the fact of that the maximum is less than this, is getting us this, right? Because we know it's the probability for one random variable under this raised to the power n. And that probability is just itself because it's uniform 0 to 1. Anyway, so this CDF function, we want to show its convergence to something not depending on n. And we found out we can just set an to bn, bn to be 1. Then this ft becomes this, and it will tend to this limit. And then we just do a little bit rearrangement. Finally, we get this result. That is, interestingly, right? This is the asymptotic distribution. Asymptotic distribution of xn bar, xn, the maximum, and for x1 to xn, IID uniform 0 to 1. Yeah, for this case. So what does this mean? You know that the maximum is converging to 1 in probability. That is something we can show. So the larger the sample size, the maximum will be closer to the upper bound of 1, right? That is a very reasonable result. But here the question is, we know 1 minus xm is shrinking to 0 in probability. but how fast does it shrink? You know, for central limit theorem, we are stabilizing that shrinking by multiplying root n, so it stabilizes. But here we need more. It's actually going to zero faster. We multiply this by n, and then the limiting distribution we just showed is exponential one. I think this is a very interesting result for you to actually play with. You can, so the good thing with computers nowadays is that you can easily numerically reproduce those results by simulation, right? You just repeat that. Essentially, you just fix your sample size n. Okay, you fix your sample size n, you can set n to be large, so the asymptotic works well. But then what you can do is that you repeatedly draw samples from uniform 0 to 1 with sample size n. You take maximum. Suppose that you do the sampling for 1,000 times, you have 1,000 maximum, and then you just plot the distribution of this and see whether that resemble an exponential one, right? You can easily check that. Okay. Second example, we still look at the maximum, except that now these IIDs are not from uniform 0 to 1, but from exponential one. Okay, and you know exponential one is a distribution without an upper bound, right, in this domain, because it can go from 0 to positive infinity. There's no actual upper bound for exponential one. Then how can we describe the behavior of this x maximum, or xn? So last time we showed you that also using the trick, we want to find an and bn, and we want to achieve something like this form. So basically, to achieve something like this form, we created an and bn. Basically, bn becomes log n. So essentially, bn is log n, an is 1. That's the form we created to satisfy the mathematical limit we want to use. But this is also very interesting, because it says that essentially asymptotically, this maximum xn increases in the rate similar to log n. Log n is increasing to a positive infinity, right? Xn is increasing similar in that rate. And therefore, you see, what we get is here. What we get is this. Xn minus log n, we don't even need to stabilize it. So their distance seem to be somewhat stable, where we don't need to scale this distance. And this follows what? A distribution called Gumbel distribution, or it's also known as extreme value distribution. So essentially, all these results we just presented to you is very useful in applications of the so-called extreme value theory. And to my knowledge, such theory is mostly used for climate science, because you really care about like rare events. And maybe it's a disaster, it's an earthquake, right? So detecting those outliers is very, very important. So therefore, I want to say that it's important to know what the application is, because for most applications, you may care about more like the central behavior, like the expectation, the mean, the average, not really the outliers. But for certain applications, the outliers is the key. So you don't really want to throw away the maximum. Yeah. Okay, that's where we stopped last time. Extreme value distribution, Gumbel distribution. You can take a look at what the distribution is like, but it's also a distribution with a positive support. So basically the range is in the positive part of the real line. So now let's move on to the third example, range of uniform sample. So now we're not just worrying about the maximum, but also the minimum, because the statistic we're interested in is this, the maximum minus the minimum. What is the range of my sample if my sample is an IID sample from uniform 0 to 1? Okay, to answer this question, we want to find the joint distribution of the minimum and the maximum, x1, xn. So, you know, we already have the result for the maximum. We just saw this. This is it. This is the result for the maximum, or this one, the result for the maximum. N times 1 minus the maximum converging in law to exponential 1. So by symmetry, what would you say about the minimum? Because, you know, the distance between maximum and 1 and the distance between minimum and zero should be symmetric, right? It's a uniform sample. So therefore, you can guess. That is, we should have n times the minimum. This one, convergent law to exponential one as well by symmetry. And this is something we can confirm. And essentially, the joint distribution for x1 and xn is what we need. Okay, so this is how we're going to find the joint distribution. Okay. For sequences AN and BN as yet unspecified. So basically we're pretending we don't know the result before. So we just start from this. So we know this x1 is shrinking to zero. It's moving towards the lower bound, which is zero. And we know this 1 minus xn is moving to zero as well. So we want to stabilize each. So AN and BN will both be diverging sequences to be specified. And this is the joint distribution, right? We need to get the joint CDF function, but we're looking at the larger than instead of smaller than. So essentially to do that, we're trying to define the range for everything. So this will tell me it's actually x1 greater than x over an, and that's the minimum's lower bound, and this is the maximum's upper bound, and xn is less than 1 minus y over bn. So this will tell me everything. Each random variable in my sample is between this lower bound and upper bound because they are IID, right? Then I can have one thing's probability to be in this range, and this is the probability raised to the power n. So it's just a way to derive this joint distribution. But of course, you need this lower bound to be above zero. You need this upper bound to be under one. You need a condition. So we already know that based on what I just said, we guessed, we can set AN and BN to be n. Then essentially, you see, when this is n and this is m, so x over an becomes x over n, y over bn becomes y over n. So this is the probability here, right? Y over n, x over n, raised to the power n. And we know that by that mathematical result, as n goes to infinity, this is raised to the power e to the minus x times e to the minus y. And what does this imply to you? If you have this, basically, you just specify, okay, I have like y1, y2 follow independently exponential one. So essentially, y1 greater than x and y2 greater than x. This joint probability will exactly be the same, exponential minus x, exponential minus y, which is the same as the limit for this joint distribution. So essentially, you start seeing that this probability is convergent to this probability. So that's what you say. This is by definition the convergence law. But it's very, very interesting in what? In that this limit, y1 and y2 are two independent exponential random variables. Essentially, we're saying that even though x1 and xn, they shouldn't be independent themselves because they depend on the same sample. However, asymptotically, xl1 and y minus xn are independent. Okay, that's very interesting, right? Like the lower bound, how far away it is from zero, and or the upper bound, how far away it is from one. That these two differences, as n goes to infinity, they become asymptotically independent of each other. Yeah, I think this is a very interesting result. And oh, let me see. Sometimes this happened. Okay. All right. So what this says is once you get this joint distribution, finally to get the range, you know the range is xn minus x1. We just place them together. And this is where we apply this continuity map theorem, or you can also consider to be part of the Slutsky theorem, depending on the textbook. So in this case, when you add up the left-hand side, the limit is the sum of the right-hand side. And you know the sum of two independent exponential one random variable give you a gamma. gamma random variable. Okay. So you derive the range, which is gamma. But of course, this range, the range itself here, 1 minus Rn, this is constrained to be what? This is going down to 0 because, as your sample size goes larger and larger, the range will be closer to the full range, right? The 1. So Rn is approaching 1 with probability. And again, you're stabilizing this shrinking difference by multiplying n. Then you have a stable gamma distribution. Okay. Any questions so far? If not, then let's look at example 4. Okay, so in this example, we're still looking at IID uniform 0 to 1 random variables. But now we're not looking at a joint distribution of x1 and xn, but we're looking at xn minus 1, which is the second maximum, and xn, which is the maximum. How are they jointly distributed? Okay, so this is more complicated. Because, if you know the maximum is under some value, then everything is under some value. But for the second maximum, it's not so easy. You need some discussion. You need to discuss, okay, where my maximum is, and where my second maximum is. And the second maximum is at what value means that, okay, n minus 1 of these n random variables are under this value, but you have one variable bigger than that, right? You need to have the discussion there. Okay, so following this example, now following the previous example, we have this. And we're still considering 1 minus because we know the maximum and second maximum are both close to 1. Okay, so if you want to get their joint distribution, this is essentially, these two things bigger than x and y. This means that the second maximum is less than this, and the maximum is less than that. You need this to hold simultaneously. That's the joint probability. As I said, you need to consider two separate cases because here the x and y values are uncertain about their order, which one is bigger. So if x is less than y, right, then this is bigger than this. Okay, 1 minus x over n is bigger than 1 minus y over n. And this is smaller. And since this is smaller, only this one matters, right? Because as long as the maximum is under a smaller value, then the second maximum must be under the smaller value. Then it's for sure under the bigger value. So we only need to consider the maximum. And that's the limit we get. But this is an easier one. But if y is less than x, then this is smaller than this. And we need to consider both. We cannot drop the second maximum condition. So in this case, this means that you can decompose this joint event into two cases. That is, first, the maximum is under the smaller value versus, and the maximum is not under the smaller value, but under the bigger value. And it's between the smaller value and the bigger value. So you just decompose the maximum into the two cases. So this first case, only about the maximum is easy. Again, it's just that everything is under this value raised to power n, probability. For this one, you know where the maximum lies in, right? You just need to consider n possibilities because any one of the n random variables could be the maximum. That's why we have the n choose one. So this means that after you choose the one, for the remaining n minus 1, they are under the smaller value. Only the last one is between the smaller value and bigger value. That's the probability you get. But for this probability, the n here can be canceled by the n in n choose 1. So you're still left with this 1 minus x over n raised to the power n minus 1, right? Yeah. So, and this one has the same limit. So let me just quickly write here. So essentially, 1 minus x over n to the power n. For this one, it converges to e to the negative x. No problem. How about for this one? The power is now n minus 1. It's the same limit. Yeah. Okay, so we're applying this result, these two results here, and that's how we get the limit for this case too. So for y less than x. Okay, so now the question is, how do we find the limiting random variables? So basically, what is the limiting distribution of this n times y minus x n minus 1, second maximum? What is the limiting random variable for this n times y minus xn? So essentially, what is your guess, actually? We know that for 1 minus the maximum times n, that is convergent to exponential 1, right? We also know that for n times the minimum minus 0, that is also convergent to exponential 1. So the hypothesis could be that maybe for the second maximum, is this difference between the second maximum and the maximum also something exponential 1. So basically the gap is exponential 1, essentially. And that's our guess. Okay, and you can actually see we can confirm this. Let's read this paragraph together. The second inequality above arise because x n minus 1 less than, this is basically this one, x by n minus 1 less than a less than x and less than b, if and only if exactly n minus 1 of the xi are less than a and exactly 1 is between a and b. That's how we do the derivation. We now know the joint asymptotic distribution of this n times 1 minus second maximum and n times 1 minus maximum. But can we describe this joint distribution in a simple way? Suppose that y1 and y2 are independent exponential 1 variables. Consider the joint distribution of y1 and y1 plus y2. That's what I'm saying. So basically, the gap between the maximum and 1 times n is exponential 1. And the gap between second maximum and 1 times n is two independent exponential 1 sum. So it's the gap between xn minus 1 and xn is also exponential 1. That's the idea. y1 and y1 plus y2. Then let's consider this joint distribution, okay? And we want to show that this joint distribution is the limit of this joint distribution. That's what we want to show. We want to show that this joint distribution's limit as n goes to infinity converges to this joint distribution. And then we can say that, okay, y1 plus y2 is the limit of the n times y1 plus y2 is the limit of this n times 1 minus second maximum, and y1 is the limit of this n times 1 minus xn. Okay. So again, we can have the discussion regarding the relationship between x and y. So if x is less than y, then it's simple because we just need to consider a second one, because the first one will for sure hold then. And for the second one, it's just exponential negative y. If y is less than x, then we need some discussion. And this is something we can also do using the definition of joint probability. We do integration, right? We're using the density function of exponential 1. That's what we get. So essentially, you see this result and this result, these two probabilities are just the limits of the probabilities we get before. This one, this one. So that's why we show that by definition of the convergence law is the convergence of a CDF function. That's why we can say that n times 1 minus second maximum converges in law to y1 plus y2, while n times 1 minus maximum converges in law to y1. So in this case, you see that the two random variables in the limit are not independent because the first one includes y1. Okay, marginally, this is what you get. So basically, it's very interesting that in that we have a result that's, gamma 2, 1 is what we previously had. me see. Where are we? Here. You see. So 1 times 1 minus the range is also converging to gamma to 1. Okay. And now we see that n minus 1 minus the second maximum is also converging to gamma to 1. Okay. The reason is because what I just said. So basically we have 0, 1. I'm just trying to draw a graph here. This is x1, the minimum, and this is the xn, the maximum, and this is xn minus 1 second maximum. So essentially, we're saying that as n goes to infinity, then this segment, this segment, this segment, they are all approaching, if you multiply each segment by n, they're all approaching exponential 1. That's it. Yeah. Okay, now example 5. Suppose x1 to xn are independent IID exponential 1 random variables. What is, okay, now you see the change is that we're going from, again, uniform 0 to 1 from previous example to this example, exponential 1. What is the joint asymptotic distribution of xn minus 1 xn? So you may wonder, why are we so interested in uniform 1, 0 to 1 exponential 1? There's a reason, actually. The reason is that, any distribution can be constructed from uniform 0 to 1. And that is how sampling works in our computer. Essentially, if you want to draw a Gaussian sample, you're basically doing what? You're basically doing uniform 0 to 1 sampling. And then you are basically, because of the CDF function, right? So Gaussian random variable, if you draw a random sample from Gaussian, you apply the Gaussian CDF function to the transformation, then the sample will become uniform 0 to 1. So the other way will work. You first get a uniform sample, then you apply the inverse Gaussian CDF function to each uniform sample, then you get a Gaussian sample. So that's why, and also these transformations are monotone. You keep the order, you only change the values. And that's why knowing how things work under uniform 0 to 1 is very, very important. Yeah. An exponential 1 will also be important for a reason you will quickly see when we try to derive the asymptotic distribution of sample quantiles. Okay, now let's look at the sample from exponential 1. And what is the joint distribution of the second maximum and the maximum? Okay, so this is the CDF function of exponential 1. This is it. We get the inverse of the CDF, and that's what it is. So we are trying to use the result we already obtained from uniform 0 to 1 to exponential 1. So essentially, what this means is, if I take a uniform sample, a sample from uniform 0 to 1, I record the maximum of that sample as UN and the second maximum as UN minus 1, based on what I just said. The inverse transformation applied to this uniform sample will give me the exponential 1 sample. And the second maximum stays as second maximum. The maximum stays as maximum. Okay, that's just it. So we can convert a uniform sample to an exponential 1 sample by using the inverse of the CDF function of exponential 1. They follow the same distribution. Okay, now I am going to apply what I have from the previous result. Remember, n times 1 minus second maximum, n times 1 minus maximum. That's what I have. And you just do the algebra here, and you essentially get it's xn minus 1 minus log n, xn minus log n. That's it. Because we already know that, let me just quickly write what we have. We already have n times 1 minus un minus 1. We just saw this. N times 1 minus un. This will convert in law to y1 plus y2 and y1. We already have that. Now we're just applying negative log to each one. That's what we get here. This is the continuous mapping theorem. And that's it. So essentially, you have y1 and y2, both independent exponential one. These transformations apply to them. That is the distribution you get. So essentially, I can tell you that this thing actually follows what we said, the Gumbel distribution. Remember that for a previous example. In previous example, we didn't go through this distribution transformation route. We do the from scratch derivation. Remember that we told you this. Let me quickly find that part. This is what we previously showed you. We showed you here. For exponential one sample, xn maximum minus log n converging log to t, where t follows Gumbel distribution. Okay, and here we're just doing the derivation again. We're saying, okay, yes, it's convergent to some negative log y1, where y1 exponential one. So essentially told you how to get a Gumbel distribution, basically. Yeah. Okay, so any other questions? If not, then we will continue. So that's mostly what we try to say about extreme order statistics. I think we covered most of what I want to say. Yes. So this is where we are at, exponential extreme order. So just to quickly wrap up, we talk about two distributions where we can derive extreme order statistic distributions, asymptotic distributions. One is uniform 0 to 1, one is exponential 1, right? Our samples are from both cases. So for uniform 0 to 1, we basically look at the difference between the sample boundary, maximum, minimum, versus the population boundary, 0, 1. And we know that difference is shrinking to 0, but we can stabilize that shrinking difference by multiplying n, and then we can show that by multiplying n, the limiting distribution is exponential 1. Okay, that's the first result. Second result, if the sample is from an exponential 1 distribution, we know that the maximum is behaving very like log n, and their differences follow Gumbel distribution. Okay, now let's don't look at the extreme order statistics anymore. Let's look at quantiles. So what is a quantile? So the quantile you are most familiar with, I think, is median. Median is the 50% quantile. Okay, let's look at this. Maybe we should spend some time to quickly read this paragraph together. Let x1 to xm be a sample from a distribution f on the real line and assume that f is continuous. F is the CDF, okay? So that all observations are distinct with probability 1. So you don't have repeated values because it's a continuous distribution. For p between 0 and 1, okay? The pth quantile of f is defined as this. So let's pay attention to this notation. This is the quantile. Quantile is defined as the value where its left tail probability is p. So essentially, it's based on this CDF function. So let me just tell you this. So you know for the CDF function, fx, x, right? CDF function takes value between 0 and 1. So essentially, we should have a CDF function like this. So suppose that here you have the CDF value as p. You find the corresponding x, and this is called xp. Another way to look at it is to look at the density function. That is, if you have the density as continuous, I'm just drawing Gaussian, for example, then what is xp? It means that when the left tail probability is p, the corresponding value is xp. That's what we mean quantile. So when the p is 0.5, then it's the median, right? Okay, so this is that. And the pth sample quantile, okay, here it is. This is the pth quantile, population quantile. Pth sample quantile is this one. It's basically an order statistic. And the order where in the sequence is based on this. N times P, you do the ceiling. Okay, you do the upper bound because you need the order to be an integer, and N times P may not be an integer. So that's the sample quantile. The smallest integer greater than or equal to N times P. If the density fx exists and is continuous and positive in the neighborhood of some quantiles, then the joint distribution of the corresponding sample quantiles is asymptotically normal. That's what we want to show. Okay, asymptotic normality for sample quantiles as estimators for population quantiles. We give the proof for 2 quantiles. The extension to many quantiles is easy. All right, now let's look at this transformation again I just mentioned. The transformation UI defined as f CDF applied to xi for I from 1 to m gives UI U1 to UN as the order statistic of a sample from the uniform distribution, right? We can basically, this is just saying this very simple fact, that is f x I follows uniform 0 to 1. That's just a simple fact. And this, to prove this, is just one line. Essentially, you just need to show that the probability f xi less or equal than t is what? The probability that fxi is less or equal than t, you want to show it's uniform, then this probability should be equal to t, right? How can we show that? You can just do this. If the inverse exists, xi less or equal than f inverse t, okay? And then as f is the CDF function of xi, then it's f at f inverse t. And that's t. So because of that, then you show fxi is uniform, 0 to 1. Okay, so we first proved the theorem for a uniform distribution. That is, the sample quantile follows asymptotic normal distribution, and then derive the general result for any distribution using the delta method. Okay, delta method will be used again. Okay, first, the joint distribution of the order statistics U1 less or equal than UM from this uniform 0 to 1 has the following well-known representation as the distribution of ratios of waiting times. This is very, very important. So we are going to create such uniform order statistics from some partial sums of exponential 1 samples, waiting times. You know, exponential distribution was used to describe waiting times. To facilitate this derivation, we begin with a quick review of changing variables. This is a probability result. Okay, how do we change variables and get the distribution or density after the change? Suppose x has density fxx and y has, okay, and y is a transformation. Y is g applied to x. And here we're talking about a vector form. So x is k-dimensional, y is also k-dimensional. Okay, so from Rk to Rk, g is a differentiable and has a well-defined inverse function, which we denote by h. So h is g inverse. It also maps from Rk to Rk. So essentially, you have y is gx and x is hy. So the question is, given the density of x, how do I get the density of y? That's called the change of variable formula. And we know that this is the result. So for the density of y, it's not just that you replace x by hy in its own density. You need to consider the so-called volume change. And this volume change depends on this derivative, the derivative of the h function at y. Okay, so essentially it's the density function about y. So everything should be about y. And the derivative h function, h function maps from y to x, right? So essentially, you're applying this transformation and you calculate density at this hy value, but you also need to consider the change of the volume at that value. And that's the density function you need to consider. So essentially, the result is the absolute value of the determinant of this. It's actually not, it's a gradient matrix basically, because h dot will be k by k, because it's a k value function, takes k value input. Yeah, and this is called Jacobian of h, absolute value of the determinant of the k by k matrix. So this is a change of variable formula, and we will use this formula to get the density. Okay, and for the following, I think it's a very interesting lemma, very important result for deriving the sample quantile asymptotic normal distribution. Let y1, 2, let's look at the lemma statement. Let y1 to y2 to yn plus 1 be IID exponential 1 random variables. And we define SI as the partial sum of y1 up to yi. So you see, we're actually adding up y1 up to yi. This is the partial sum. And then xn plus 1, xn plus 1 is the full sum. We add up everything. So we're looking at this conditional distribution of S1 over Sn plus 1 up to Sn over Sn plus 1. So what is the range of each ratio? So you're taking sums of IID exponential 1 random variables. What is, exponential 1 random variables are all non-negative, right? Positive. And so, as you add more, the partial sum will be bigger. So that's why Si will for sure be less or equal than Sn plus 1. And you will also have S1 less or equal than S2, less or equal than Sn, right? So essentially, you're having an increasing sequence here, and each element is under 1 and bigger than 0. The range. And we're just telling you that this n-dimensional vector, conditional on Sn plus 1, the denominator, it follows the same joint distribution as the order statistics U1 to UN from uniform 0 to 1. So this is a very, very interesting result. So essentially, working on order statistics, as you have seen, is not easy, right? We have to do that derivation. But this one shows that you can actually have the partial sum ratios representing the distribution of order statistics. Okay, and how do we do it? So the proof will be showing that they share the same density. So the conditional density of this, the joint density conditional on Sn plus 1 is the same as the joint density of this U1 to Un, and they are the order statistics. Okay, so we'll use the change of variable of density functions, that formula, this formula here, again and again throughout this proof. So first of all, simple thing, get the density of y1, y2 to yn plus 1 based on their IID properties. So that is, you multiply the density of each of them together. So you get exponential negative sum yi, I from 1 to n plus 1. But of course, you need to have the constraint. Each one must be positive, right? That's the definition of exponential density. Otherwise, if it's not positive, the density is 0. Then we do the change of variable thing. We want to change y1, y2 to yn plus 1 to s1, s2 to Sn plus 1. Okay, and how do we do the map? And so, the thing we're going to change it to is called h, just like here. Here, we are going to have x with known density, That's what we have, right? We have the y1, y2 to yn plus 1 with a known density. The thing we want to get the density for is called y. And we have x equals to hy. So following that, we write y1, y2 to yn plus 1 equals to h of the things we want to get density for. S1, S2 to Sn plus 1. And because we know the S's are partial sums, then essentially y1 is S1. y1 is S1. y2 is S1, S2 minus S1. We write minus S1 plus S2. Finally, yn plus 1 is minus Sn plus Sn plus 1. That's how we can just get y1 to yn from S1, S2 to Sn plus 1. And we can easily calculate Jacobian in this case for this h. For this h, and that's just 1. So therefore, the density of this S1, S2 to Sn plus 1 is just equal to, Jacobian is 1 means that you can ignore it. It's just the same density that you just replace x by hy. And in our case, here we're replacing this based on s. And that's just minus Sn plus 1. Because Sn plus 1 is the sum of yi from I from 1 to m. And here we have each yi to be positive. This translates to the s's follow a strict order, right? S1 is the smallest. It's non-negative, it's positive. It's less than S2, less than up to Sn plus 1. Okay, we'll first get that. We get the density for s's. Now we need the density for the ratios because we want to get a density for these ratios. So therefore, we define zi to be si over Sn plus 1, the ratio. Okay, so now the question is, how do I get the density for the ratios? And we need conditional density here. So it's the ratio. You see, after my writing now, this becomes z1 to zn. Okay, but what I'm interested in is this z's conditional Sn plus 1. I need a density for that. So to get this conditional density, I need to have the joint density. So that's why here I'm interested in the joint density of z1, z2, zn, and Sn plus 1. And I want to see how I can get there based on the density of S1, S2 to Sn and Sn plus 1. This is something I already get over here. So here the question is, what is g function? How do I reconstruct S1 based on these z1, z2, zn to Sn plus 1? And because it's a ratio, right? Z1 is a ratio. So I know like Si is just Zi times Sn plus 1. So that's why S1 is just Z1 times Sn plus 1. S2 is Z2 times Sn plus 1. Sn is Zn times Sn plus 1. Finally, Sn plus 1 is Sn plus 1. Okay, and we just need to calculate Jacobian for this G. And it turns out it's just this. Sn plus 1 raised to the power n. That's the Jacobian, because we're going to apply Jacobian to this set. Okay, then you have the density transformation. So the joint density of Z1 to Zn and Sn plus 1 is the Jacobian times the density of S1, S2 to Sn plus 1. And that's what? That's exponential minus Sn plus 1. And we keep it here. And the condition, this is the previous condition, that is the partial sums follow a strict increasing order. We now change the condition to that, okay, the ratios follow a strict increasing order from 0 to 1, but the total, the denominator must be positive. So we translate that. Okay, we get this joint density. We're one step closer to the final result, conditional density. Then we need a density of Z1 to Zn given Sn plus 1. To get that conditional density, we need to first get a marginal density of Sn plus 1 alone. Then we can just do the joint, divide by marginal to get a conditional, right? The sum of n plus 1 IID exponential 1, we know the result. It's just gamma. Gamma n plus 1, 1. So therefore, the density of this one can be written out based on the gamma density. That's it. 1 over n factorial Sn plus 1 raised to the power n, exponential negative Sn plus 1, indicator function is positive. So once we do the conditional density calculation, it's the join over the marginal. We cancel everything except this n factorial. So we actually have n factorial times this indicator function that z1 to zn are between 0 and 1. What is that? This is exactly the order statistic of a sample n from uniform 0 to 1. Why is that? Because, for order statistic, this is the target. Order statistic u1 to un, the sample is from uniform 0 to 1. So you know that in the sample, each draw has density 1, right? Density 1. So multiplying n of them together is still 1. But given the same order statistic, the sample could have how many possibilities? N factorial possibilities. You have n factorial samples that give you the same order statistics. That's why we have this n factorial thing. Okay. Okay. Yeah. So that's why we have, and they follow the order. That's why. Yeah, so I think we can stop here for the first lecture because that's pretty much it. But as I said, we will continue with the second lecture. So if you can stay around, and then I will continue after a short break. But if you have to go, then you can watch the recording. Yeah.
Can also be
Let me stop the recording.